Hi everyone. Today we are going to be covering section 10.7 from the textbook, which is going to talk about the root and the ratio test. So the root and the ratio test kind of fill this gap in our knowledge of tests that we have so far. So some problems that might arise that we can't solve right now are things, for example, where the integral test, we just can't take integrals of them. So for example, something like k equals 1 to infinity of 1 over k factorial, right? Where k factorial is k times k minus 1 times k minus 2 all the way down to times 1, right? I have no idea what the integral of k factorial is. It doesn't really even seem to be defined on things that aren't integers, right? So this is something that we couldn't possibly take the integral of, and there's really no easy thing to compare it to as well. Other problems that we have with the tests that we know already is the only test that we know for dealing with negative terms is the alternating series test. But in cases where we have something like k equals 1 to infinity of something like sine of k over k, right, this has some negative terms, right? Sine of 3 is going to be negative, for example. But it's not alternating like alternating series, right? We might have runs of two terms in there which are both going to be negative or which are both going to be positive. So this would be an example where we couldn't use the alternating series test, and because the integral test and comparison tests only work for positive terms, this is something that we just don't know how to actually tell whether it converges or diverges right now. Okay, so we are going to introduce these two new tests, the root test and the ratio test, and these are going to be able to work on a more broad range of applications. They end up being slightly more difficult than the other tests. They're not too bad in and of themselves. They will involve taking some limits, but they do offer this wider range of applications. So as a general rule of thumb, you should maybe try to work through problems from tests that look easier to tests that look harder for whatever you think are easy and difficult tests for you. And this definitely varies from person to person. Okay, so we're first going to talk about the ratio test. Or let the kitty in. Okay, ratio test. So we're going to define this r, which is called the radius of convergent, as the limit. K equals k going to infinity of our ratio of our terms. So ak plus 1 over ak. And then we need an absolute value here. And then we have three different cases. We have r less than 1. The series is going to converge. And the series I'm talking about in this case is the standard one, k equals 1 to infinity of ak. So for r less than 1, the series is going to converge. And even more powerfully, it's going to converge absolutely. Absolutely. For r greater than 1, it's going to diverge. So the series will diverge. And for r equals 1, we have no info. No information. Okay, so what we need to do for this test is we need to calculate this limit right here of this absolute value. And this is fairly nice too, right? We have no need to compare terms, right? We don't need to see that they're increasing or decreasing. We don't need to see that they're always going to be positive or always going to be negative as well. The only thing that might cause some difficulty is this absolute value sign if you do have some negative terms. But in the end, that ends up being not too bad to deal with. Okay. So one important thing to note about the ratio test is the ratio test only shows absolute convergence or divergence. So it's never going to be able to pick up on these cases where we have something that doesn't converge absolutely but does converge conditionally. That's just too fine of a refinement for the ratio test. So if you suspect you have a series that might work like that, then what you need to do is use a different test in this case. The ratio test won't work for that. Okay. So let's go through 3 quick examples of problems that we can use the ratio test on. So example 1. K equals 1 to infinity of 10 to the k over k factorial. Right, this isn't something that we can take integrals of. It's not immediately clear what we want to compare this to, so the ratio test is going to be a good idea for this. So what we need to do is we need to calculate this r, which is going to be the limit as k goes to infinity of 10 to the k plus 1 over k plus 1 factorial, all divided by 10 to the k over k factorial. Okay. Note that I did drop the absolute value signs right here. That's completely okay because each of these terms are positive. So when you divide a positive number by a positive number, you'll always get a positive number out. So we're trying to calculate this limit. Let's get it just in terms of a single fraction, and then we can calculate what this limit is actually going to be. So if we multiply the top and bottom by k factorial, what we're left with is, for part of it, is this k factorial over this k plus 1 factorial. And if we go back to the definition of these factorials right there, this k factorial is k times k minus 1 times k minus 2 all the way down to times 1. And k plus 1 factorial is k plus 1 times k minus 1 times k minus 2, again, all the way down to 1. And what we can notice with this is that the k's are going to cancel, the k minus 1s are going to cancel, the k minus 2s are going to cancel. All of the terms are going to cancel except for this k plus 1 on the bottom. So this is going to cancel, these are going to cancel, and we're just left with this 1 over k plus 1. So we have that this is the limit as k goes to infinity of 10 to the k plus 1 over k plus 1 over 10 to the k. These factorials are a common reason to use the root test, and a big reason this is because we're doing this division here where a lot of the parts of the factorial are going to cancel. So in general, if you do see a factorial within your problem, it's a good idea to at least attempt the ratio test on it. It tends to be the one that's the most successful most of the time. Okay, so we still have a fraction over a fraction. If we multiply the top and the bottom by 10 to the k, or 1 over 10 to the k, excuse me, times 1 over 10 to the k, times 1 over 10 to the k. Right, 10 to the k plus 1 divided by 10 to the k will just leave me with a 10. And so this is going to be equal to the limit as k goes to infinity of 10 over k plus 1. And now this is something that we do know how to solve, right? As k gets bigger and bigger and bigger, this limit here is going to go to 0 because we're dividing by a bigger and bigger number. So this is going to be 0, which is my r value. So I am in this case where my r is less than 1. It's going to be 0. And so I know that this series converges absolutely. Okay, great. So this is an example where we wouldn't have been able to use any of our other previous tests on this problem. Let's do another one. So example 2. K equals 1 to infinity, negative 1 to the k to the k over k factorial. So in this case right here, you could possibly attempt to use the alternating series test on it. However, this would involve taking the limit as k goes to infinity of k to the k over k factorial, which is not necessarily easy to take the limit of. So instead, what we're going to do for this problem is we are going to use the ratio test and see if we can get information from it. So we're looking at the limit as k goes to infinity of the absolute value. So what the absolute value will do in this case is it will get rid of this negative 1 to the k term right here. So we have a k plus 1 to the k plus 1 over k plus 1 factorial divided by k to the k all over k factorial. My cat has this spring toy that he absolutely loves playing with. So if you hear something bouncing around in the background, he is playing right now. So that's what that noise is. There he goes. It's very cute. Okay. So again, we'll try to write this as a single fraction so that we can evaluate what this limit is going to be. So this is going to be times k factorial times k factorial. Again, as we talked about before, this k factorial right here divided by k plus 1 factorial is going to be 1 over k plus 1. And so this leaves us with the limit as k goes to infinity of k plus 1 to the k plus 1 over k plus 1 over k to the k. Okay. So now we have a k plus 1 to the k plus 1 over k plus 1. We can cancel these, and we are left with one less factor of the k plus 1 there. And so this is equal to the limit as k goes to infinity of k plus 1 to the k over k to the k, so k plus 1 over k to the k. Okay, so a big thing in these problems is the algebra does tend to get a bit nasty from time to time. So just be very careful when you're going through these steps, especially because a lot of times you'll have 3 or 4 fractions within your problem. Rewriting this slightly, we have the limit as k goes to infinity of 1 plus 1 over k to the k. And if you remember back from your Calculus 1 days, we actually were able to evaluate this limit, right? This limit evaluates to this indeterminate form of 1 to the infinity, but we actually know that this is going to be equal to e, right? In general, we have the limit as k goes to infinity of 1 plus a over k to the k is going to be equal to e to the a. This ends up coming up a lot in the ratio test just because you're dividing and you might have this power of k there. So expect to see this from time to time in this section. But we know that this limit here is going to be equal to e. E, right, 2.718 is certainly bigger than 1, so my series is going to diverge. So this series here, example 2, is going to diverge. Excellent. Okay, so these are 2 examples where we couldn't possibly use any of the tests that we have done before. In example 2, you could get around using the alternating series test, but the ratio test works perfectly well, and it does give us that the series diverges. Okay. So I'm going to now introduce the second 2 tests of this section, which is the root test. The root test is very similar to the ratio test, and yeah, let me just write it out and then we can talk about it. Root test. So I'm going to define this row as the limit as k goes to infinity of the kth root of the absolute value of a k. Right, so again, this row is going to be limit of something dealing with terms in our series. And again, we're looking at the series from k equals 1 to infinity of a k. And our conditions for the root test are actually the exact same. So if rho, which is just some Greek letter, it kind of corresponds to r in Greek, so it makes sense we'd use r and rho for our root and ratio test. So if rho is less than 1, the series converges absolutely. Rho as greater than 1, it diverges, series diverges. And again, for rho equals 1, we have no information. So, in general, if you can prove things using the root test, you can prove them using the ratio test, but not vice versa. So the root test, which actually I think is something they don't even talk about in the book, but the root test will always give you a stronger result than the ratio test. So what I mean by that is that this kind of range of values where my rho is going to be equal to 1 is smaller in the root test than in the ratio test. It is able to determine a few more sequences in this case. Now, an important thing to note, though, is that kth roots can be difficult to calculate, right? It's not something we generally talk about a lot in math. There aren't a lot of good rules for dealing with these kth roots right here. So this stronger property of the root test comes at the cost of this limit being a lot harder to calculate. So most of the times when we do use the root test is we're going to have some part of our series raised to the kth power, because then we'll be able to at least cancel part of the raised to the kth power here, or to the 1 over k here. So as an example of this, I think this is example 3. Let's look at the sum from k equals 1 to infinity of 3 minus 4k squared over 7k squared plus 6. Okay, so this is a great idea to use the root test on because we have this raised to the k. And so when we take our sequence and take a kth root of it, this k is just going to go away, which is kind of what we want, right? We want, we want this k to go away, and so we can just deal with what's on the inside part right here. So we are left, if we're using the root test, with the limit as k goes to infinity of the kth root of 3 minus 4k squared over 7k squared plus 6, all raised to the k. Again, as I mentioned before, the kth root and the k are going to cancel, and so we're left with the limit as k goes to infinity of 3 minus 4k squared over 7k squared plus 6. Okay, now in this case, right, we would like to get rid of this absolute value so we can use our rational function technique, right? We're kind of expecting a 4/7 here because we have a -4 and a 7 here. We note that for k big enough, this -4k squared is certainly going to be overpowering the 3 here. And furthermore, the bottom is always going to be positive, so we have a negative number over a positive number. And so taking the entire function as negative will allow us to get rid of this absolute value. So in particular, this is equal to the limit as k goes to infinity of 4k squared minus 3, 7k squared plus 6. And again, this is a case we know how to deal with, right? It's a rational function. we have a polynomial over a polynomial, and even better, the polynomials have the same degree. So we have this 4k squared over 7k squared, which is going to translate into 4/7. This 4/7 is our row value. Row in this case is less than 1. 4/7 is less than 1. And so this series here is going to converge absolutely. Okay. So this is a great example of when you can actually use the root test. And let's go through one more. And actually it's going to be another example where this limit I have boxed up here shows up, where we're going to get some ease in our answer, which also kind of makes sense showing up with the root test, because I have this kth root right here, and this is raised to the k. Okay, so let's look at the sum, or this is example 4. This is the sum from k equals 1 to infinity of -2 to the k over k to the 10th. Now, if we do pull out a -1 out of here, we could use our alternating series test to tell whether this is going to converge or whether this is going to diverge. But let's use the ratio test, or sorry, the root test on this just to show that it works. Because as with a lot of things in math, and I think this is something I've tried to stress a lot over the summer, is that you can always do things a couple of different ways in math, right? So in this one, there's a few different techniques you can use for this, but let's actually show what the convergence or divergence is going to be using the root test in this case. Right, so we're looking at this row, which is going to be the limit as k goes to infinity of the kth root of -2 to the k over k to the 10th. Okay, well, taking kth roots, right, that's going to get rid of this k power right here, and so we're left with the limit as k goes to infinity of -2 over k to the 10 over k. Okay, so this right now is not something that we necessarily know how to take the limit of, right? We have this 10 to the k and the k here. So what's going to happen is we're going to get this 0 over, this infinity raised to the 0th power. And this is one of those indeterminate forms where it's not actually going to tell us what the limit is equal to. Okay, so we can rearrange slightly. Oh, I did forget absolute values here. So the absolute values here are going to get rid of this -2. And sorry, I did actually misspeak before. This is not one of those integrals, one of these series where e will come into play. I was thinking of a different example from a different lecture. Instead, what we're going to do is we're going to use the fact that the limit as k goes to infinity of k to the 1 over k is going to be equal to 1. This is another of those important limits that you should have written down somewhere, because it, as in the one with ease, this one is going to come a lot, especially if you are using the root test a lot, because we have this 1 over k in it. This is something that you can prove using, I believe, natural logs and a version of L'Hopital's rule to prove it. And at least when I was TAing for Calc 1, it's something that you went through in Calc 1. So you can always refer back to your Calc 1 lecture notes to see why this is true. So rewriting this is the limit as k goes to infinity of 2 over k to the 1 over k raised to the 10th. right? And the reason we're going to do this is that this bottom part is going to evaluate to 1, and so the entire thing is going to evaluate to 1 to the 10th, or just 1. So this limit is going to be equal to 2. Well, the limit is 2. 2 is certainly bigger than 1, so we're in the case where rho is bigger than 2, and our series diverges. So this series right here diverges. Okay, great. And this does kind of make sense, right? I have an exponential over a polynomial. Exponentials, this 2 to the k, grow significantly faster than polynomials in all cases, and so the top's going to be getting bigger, while the bottom's going to be getting bigger, but a lot more slowly. So this 2 to the k will kind of overpower the k to the 10th we have right here. Now, one important thing that I do want to note for these problems is this rho and this r value is not actually what your series converges to. So for example, 3, right, we got the rho as 4/7. That does not mean that this is what the series converges to. The series will, I have no idea what this series converges to actually. I'm guessing it will most likely have possibly pi's in it, because pi's tend to come up a lot in these series, but rho is not what your series converges to. Much like all of the other series convergence and divergence tests, they're not going to actually tell you what value you get if the series does converge. That is a fairly difficult field of mathematics. We'll talk about it a bit in the next chapter when we talk about Taylor series as well. But there's a lot of different techniques for determining what these series are equal to, and it's just something that we can't properly cover in Calculus 2. We're just more interested in whether the series are going to converge